So this is the second video on Chapter 30, Rates of Change. And so I'm going to look at example 243, example 244, which I'm going to work in two different ways. Neither one is exactly the way it's done in the notes. And then we'll talk about the difference between speed and velocity. So example 243, we have a population of a community is growing according to this model, where t is the time in months. And we want to know what is the rate of change of the population after 5 months. Well, the rate of change of a function is the derivative. So we calculate the derivative. We want to know the rate of change at time equal to 5, so we substitute 5 into the derivative, and we have 1400. So according to this model, this community is growing at a rate of 1,400 people per month, which is granted a very high growth rate for a community. Example 244, we've thrown a stone into a lake and it's making a circular ripple. And the radius of the ripple is increasing at a rate of 2 centimeters per second. And you're going to notice that when you look at the problem, I made a little note here. The rate of change of the radius is 2 centimeters per second. That's really what we need to know to start the problem. So I've written down the relevant information. We know that the area of a circle is pi r squared. And we know that r is 2t. Why? Because the radius is increasing at a rate of 2 centimeters per second. So r is 2t. So there are two solutions to this. The first one is we're going to write the area as a function of time. So we substitute 2t in for r, and so we have the area is 4 pi t squared. And then we want to know the rate of change of the area with respect to time, so we calculate the derivative of the area with respect to time. In the notes, you'll notice that I wrote a of t is this function and a prime of t. That's just different notation. It's the same thing, but here we have the derivative of the area with respect to the variable t. It's 8 pi t. We're given in the problem that t is 3. So we want to know the rate of change of the area at time 3, so we substitute 3 for t, and we have 24 pi centimeters squared per second. Area is measured in square units. This is one way to do the problem. We wrote the area as a function of t. Another way to do this is to use the chain rule. So we have area as pi r squared. We want to know the rate of change of area with respect to time. What does the chain rule say? That says that's the rate of change of area with respect to radius. In other words, dA dr multiplied by dr dt. This is the chain rule. So we have the r as the inside function and the a in terms of r as the outside function. So we're using the chain rule here. We'll be a little bit more comfortable with this, hopefully, when we get to related rates. So here we have dA dt is dA dr times dr dt. dA dr, because a is pi r squared, the derivative of a with respect to r is 2 pi r. What is the derivative of r with respect to t? Since r is 2t, the derivative of r with respect to t is 2. So the dr dt is 2. So we write this as 4 pi r. T is equal to 3. We're given that in the problem. So we want to substitute r when t is equal to 3. But remember, r is 2t. So if t is equal to 3, r is equal to 6. So we substitute 6 for r, and we have 24 pi. So the rate of change is 24 pi centimeters squared per second. I didn't want to make a video for part 3, so I'm going to just talk about speed and velocity momentarily. Velocity has direction associated with it. So velocity can be positive or negative or 0. So velocity is positive, negative, or zero because it has direction associated with it. Speed does not. Speed is the absolute value of velocity. So speed is always greater than or equal to zero. So speed is the absolute value of velocity. Velocity is positive or negative. So imagine you're in your car and you're just driving back and forth in your driveway. When you're going forward, your velocity is positive. When you're going backward, your velocity is negative. Your speed is always greater than or equal to zero.